Okay, today we are talking about the general rules of probability. Um, and quick review of yesterday. Rule number one says all events have a probability between, including 0 to 1. So the any event has a probability between 0 and 100%. Doesn't matter what that event is. The probability of that sample space is always one. So sample space, remember, being all the possibilities. The probability of all the possibilities when I add them together is one. The probability of a complement, that means not A. So example of A complement would be seniors. If event is seniors, probability of being a senior, A complement would be not a senior. The probability of A complement is always 1 minus P of A. Very powerful rule. Um, Rule 4, if A and B are disjoint, meaning there's no overlap, probability of A or B means add them together. Okay, disjoint, sometimes disjoint is called mutually exclusive. We will add to this and modify this rule later today. If they are independent, this is important, only if they are independent. This works both ways. If this rule is true, then they are independent. If the rule is not true, they are not independent, even if they seem like they might be. Okay? So that's P of A and B equals P of A times P of B. Multiply the probability rules. So, union. Union means it is in at least one event. That means we add them all up. It's the same as or. Or and union go together. In the case of these disjoint, as shown in this Venn diagram, P of A or B of C or C, just add them all together. So that these rules kind of extend to beyond two. Usually we show the rule in the case of two, but they often extend beyond. So a uniform distribution, generating a random number between 0 and 1. What is the probability that the first digit will be odd? So if the first digit is odd, it falls into this block between 0.10 inclusive to 0.20 but not inclusive. So that's 0.19999, etc. And we can see these bands highlighted in the graph. Each one of these has P of, we'll call this A, this B. P of A is, if it's random, it's equal probability. They're all 0.1. I've got 5 of them that are 0.1. So that is 0.5. We would expect half the time we'd expect a randomly generated number between 0 and 1 to start with a odd digit. Okay, but what if they overlap? This is a case where they are not disjoint. Okay? And this becomes, so we just add them together, but then we subtract the overlap. And the reason we subtract the overlap, when we do P of A, we do all of this. When we do P of B, we do all of this. Notice that I've counted the overlapped area twice, so I'm subtracting that. If the events are independent, P of A and B becomes P of A times P of B. But that only applies if they're independent. So this general one for adding two events, P of A or B, is P of A plus P of B minus P of A and B. If they're disjoint, you add P of A plus P of B, your P of A and B is 0. So it really still fits into this rule. Um, and here is the rule, just using union and intersection symbols. Intersection meaning and, union meaning or. So, probability of a promotion. Okay. Deborah and Matthew are anxiously awaiting word on whether they have been made partners of their law firm. Deborah guesses that her probability of making partner is 0.7 and that Matthew's is 0.5. So that means P of D equals 0.7, P of M equals 0.5. The assignment of these probabilities not give us enough information to know the probability that at least one of the two is promoted, because it would add to 1.2. That's not possible. If Deborah guesses that both, again, these are all her guesses, but are promoted, that would be 0.3. So the probability that at least one is promoted is 0.7 plus 0.5 minus 0.3, or 90% chance. If the probability that neither is promoted, I'm going to use this complement rule. Or 1 minus 0.9 equals 0.1. And many of you could probably do that one without actually writing out the rule. You can just see it, but it becomes important to remember that rule because it applies in lots of fun situations. Okay, Venn diagrams become very helpful in this. These add to 0.7. These add to 0.5. If I add them all up, I'm left with 0.01 left. Sometimes these are called joint events or joint probability. This is it showed as a two-way table. I like the Venn diagram way better. Okay. Although I don't love the notation here on the. So this D and MC means Deborah and not Matthew, Deborah and Matthew, not Deborah and Matthew, not Deborah and not Matthew, with those complements. That's also what shows up in this table. Okay, conditional probability. Conditional probability means probability of something given you have an event. So, Slim, we're going to talk about Slim a bunch. Slim is a professional poker player. He stares at the dealer who prepares to deal. What is the probability that the card Slim is dealt is an ace? There are 52 cards in the deck. Because the cards are carefully shuffled, each is equally likely. There are 4 aces, so that is 4 out of 52. And that is 1, so 1 out of 13. Important thing to note when doing probability with cards, I might be dealing to 5 players. I can see the cards in my hand. I can't see the cards in anybody else's hand. I don't know what they are. So the chance of those cards being something different is the same chance that they're in the deck. So we treat the cards in other people's hands as if they were in the deck for probability. It's pretty simple. it functionally works out to be the same because we can't see anything. Okay, so this calculation assumes that Slim knows nothing about any cards that are already dealt. Suppose he is now looking at four cards in his hand, and one of them is an ace. He knows nothing about the other 48, so they're just as equally likely in the deck as they are in somebody else's hand. Slim's So we want to know the probability that Slim gets another ace. So it's notated here, Slim probability of ace. This little vertical line here is given. He has one ace in his hand among the four cards he sees, meaning he has three aces available out of the other 48 cards, where he has a 1 out of 16 chance of getting an ace. That's called conditional probability. It's read probability of A given B. And that means the event B has happened, or we know it's going to happen, something along those lines. And we want to know the event, the probability of what would happen next. Okay, marital status of women. This diagram shows the marital status of women broken down by age group. For the United States, I think this is in thousands of women. And this is from 1999. So A is the probability a woman chosen is young. That's 18 to 29. B is the probability that the woman is married. So probability of A is 22,512 over. So I'd look at my table, I go 22,512 over the 103,870. The probability that they are young and married, again, my total stays the same, but my young and married this is the group that is young and married, 7/8 over the 103,000 total. Well, what it's going to ask me for next is B given A, which is married given young. And it's young and married, that chunk, over the young chunk. And so we get much higher probability here. And again, I'm just reading these numbers right out of the table. This one, I happen to have them above, so. So anytime you have a table, look at your B given A. So I'm looking at B and A, and you'll see this in a formula. The spot that is B and A, and you'll divide it by the probability of, or by the total number of young women. So this is young married women divided by young women. This is it written in a different form. Here's the form that I just wrote it in. This is an important formula. I would recommend putting it in your notes in case you're not given a table. Because if you're given a table, don't use the formulas, just use the tables. But if you're not given a table, then you need to use that formula. So, Slim is still at the poker table. At the moment, he wants very much to draw two diamonds in a row. As he looks at his hand and the upturned cards, maybe he's playing Texas Hold'em where there's certain shared cards. Slim sees 11 cards. Of these, four are diamonds. A full deck contains 13 diamonds among its 52 cards, so 9 of the 41 unseen are diamonds. Slim wants 2 diamonds, so he gets 9 out of 41 as his first. The probability of his second, now he's got one. There's now only 40 cards left and only 8 diamonds left, so he gets 8 out of 41. It's important to recognize that once he gets this first card, that's no longer available as a diamond or a card, so both those numbers need to change. You multiply them to get the probability that he gets 2 diamonds. 0.044. So possible, low probability, but definitely within that, this happens. So this is again, you can use the formulas. This is using the table that we used before, but I recommend just using the tables whenever possible. So what they're showing is they use the table to generate these two. So we get this division. And when we divide fractions, we multiply by the reciprocal of the bottom one, and those cancel. And we end up with this. That's some of the basics of conditional probability. Now we're going to move on to the not so basics. So the intersection of any is the event that all events occur. Okay. This one's going to show up a few times. Only 5% of high school basketball, baseball, and football players go on to play at the college level. Of these, only 1.7% enter major league college sports, and about 40% of athletes who compete in college and then reach the pros have a career more than for 3 years. So the probability of A is 0.05. Probability of B given A is 0.017. Probability of C given A and B is 0.4. So if we want to know the probability that a high school athlete is going to have a pro career of more than 3 years, well, I've got this times that they even go pro, that's that, times that they last on the pros, and I get 0.00034. So that's 0.034%, way less than 1. Okay. Not a good chance, but when we were in high school, we all still dreamed of it. Okay. So tree diagrams, a future in professional sports. So now we're just going to go to making it to professional sports. Male high school athlete plays in college, 0.05. College and goes pro, 0.017. Doesn't go pro, 0.983. So to get this, I go 0.05 times 0.017. To get this, I do 0.05 times 0.983. And I can get values for that. Now we've got male high school athlete does not compete in college, but does go pro. 0.95 times 0.0001. 0.95 times 0.9999 is doesn't compete in college or the pros. So there is this alternative route to the pros where you just go straight there without competing in college. That happens somewhat significantly in baseball as you get drafted to the minor leagues. Used to happen some in basketball. Players like Kobe Bryant, LeBron James went straight out of high school to the pros. But I think they don't allow that anymore. You have to go to college for at least a year. So if I want the probability that a male high school athlete makes the pros, I take this one, but I also have to add that to it, which does raise my probability. I mean, both are very low probabilities. It's not quite the same value we had before because we don't have the lasts for 3+ years. But when I add them together, I get this, which is definitely a significant bump from that. About 9 high school athletes out of 10,000 will play professional sports. Not a good shot. Um, if you apply this, you can use this very long rule called Bayes' rule. I recommend just doing this with tree diagrams instead, but you can. I think it's too hard. So I'm going to show you one that doesn't really apply nicely to Bayes' rule, but a tree diagram makes sense. So we're going to analyze, should this person get a kidney transplant? And now this is old data, but so Lynn has end-stage kidney disease, and if her kidneys have failed and she cannot survive unaided. About 52% of people survive on dialysis for 3 years. This might have gone up, but so she's got this option of dialysis. 52% of the time she'll last 3 years, 48% of the time she'll die in under 3 years. We don't know exactly how long. Lynn, however, is eligible for a transplant. Now that's a big surgery. So she wants to know what is her odds of living longer than 3 years with a transplant? Well, if she gets the transplant, 96% of the time it's successful after 1 month, or it appears to be successful after 1 month. It's working. 3% of the time it's not, and 1% of the time you die within that month. If you are not successful in this 3%, you go back onto dialysis. You get the same survival rate that people that didn't have a transplant had on dialysis, and the same death rate. Um, if you were successful at 1 month, 82% of those are still successful at 3 years. So you've got a 78.7% chance. That's pretty good. That's a lot better than your 52%. Some of those that were not, notice they have a problem and go back to dialysis. Because they're doing this somewhere in the 3 years, they actually end up with a higher survival rate at 3 years and a lower death rate because maybe they were only on dialysis for 1 or 2 of those 3 years after their transplant. And 10% of those die without going back on dialysis, maybe by choice, or probably in a lot of cases, they don't realize their kidney is failing again in enough time. So, if I want to know the chance of Lynn making it 3 years getting this transplant, I'm going to add all of these survive numbers together, and I've got them all underlined. So this is a important way to draw this, and we just put the probabilities on each one. When I add them up, um, that is, I don't know. It's written down here. Okay, here it is. Just erase. So here it is. We add all three of them together and we get 85% chance. That's a lot better than the 52% chance. And there's a 78% chance that she's not going to have to go to the hospital once or twice a week for dialysis. So the surgery is major, will take initial recovery time. It's going to be worse than dialysis at first, but there's a good chance that she won't even need dialysis and will be much better. And the chance of her living 3 or more years really goes up. Now, the probabilities do not entirely make the decision, but the probabilities did give us a good option for making that decision and knowing more information about how good is this surgery. Okay, that is the end of section 6.3 and the end of chapter 6.